Greetings of the day, dear students. In this video, we are going to discuss about the types of DC machines, right? Based on the excitation used, depending upon the type of the excitation used, and the DC machines are mainly classified into self-excited and separately excited, right? And again, in self-excited case, we are having series wound, shunt wound, compound, and again in compound we are having short shunt and long shunt. And with respect to the generators, we can observe in dear students, in series wound the field winding is in series with the armature, but whereas in shunt wound the field winding RSH is in parallel to the armature. And in compound wound, if it is short shunt, right, this RSC is in series to the load terminals, and of course RSH is in parallel with the armature. In long shunt, RSC series field winding is in series with the armature, and shunt field winding is parallel to the combination of armature and series field winding resistance. In this diagram table, right, EG indicates the generated EMF, V is the terminal voltage, and IA is the current flowing in the armature. Of course, this armature in series wound, armature, series field winding, and load all are in series. Therefore, whatever the current that is flowing in armature, IA is same as the current flowing in the field winding. ISC is same as the current flowing to the load. When if it is series generator. Similarly, if you observe the shunt wound, at this point, if you apply the KCL, whatever the current is generated from the generator, armature, IA, some part of current is flowing to the field winding and remaining part will flow to the load. Remaining part of the current will flow to the load. Therefore, out of the total current generated, IA, it is getting divided into shunt field winding, ISH plus I. Right. Similarly, in compound wound, we can observe that at this node point, if we apply the KCL, out of the current coming from the generated from the generator IA, it got split up into two parts. IA is equal to some part is going to the field winding and remaining part to the series field winding and to the load. Right. IA equals to ISH plus ISC in series in this short wound. If you observe in long shunt, observe here at this node point, the series field winding is in series with the armature. Now, whatever current that is coming from the armature is also flowing in the series field winding. At this node point, if we apply the KCL, the entering current is equals to the sum of leaving currents ISH plus I. So, dear students, please observe. These are the different types of DC machines. All these are the things with respect to the generator. With respect to the generator, here one more thing. If it is separately excited, the field winding is given supply by some means of external DC supply. Here we are having some external means of DC supply. Through this, we are going to get the help of this DC supply. The field winding is excited. Because of that, the current IF will flows to the field winding. Now we are going to have a variable resistor. With the help of this resistor, we can change the current flowing in the field winding. Right? Now, if you observe here, the generated voltage EG, and the current flowing in the armature is IA. That same current is flowing to the load V. Load terminal voltage is V. Terminal voltage is V. EG is the generated voltage. IA armature current, IF field current, right? Now, similarly, with respect to the DC motor, what happens is Of course, you know the purpose of the motor, which converts the electrical energy into mechanical energy. It takes electrical as input voltage or current. We will apply the voltage to the motor. Now, here also, depending upon the excitation, we are having self-excited and separately excited. In self-excited, again, series wound, shunt wound, compound wound. Compound wound further divided into short shunt, long shunt. Now, the difference in these diagrams you can observe. The current is into the armature. Observe here. The terminal voltage V is applied. Terminal voltage V is applied to the motor. Now current I flows. If it is series, the same current is flowing in the series field winding RSC. It is also flowing in the armature. Therefore, here also I equals to ISC equal to IA. The current flowing in the armature and in the field winding, series field winding, and in the load. Sorry, not the load here. To the motor, applied voltage. The current drawn by the motor. All are same. All are same in series wound. In shunt, now observe here. At this node point, whatever current that is entering, the current drawn by the motor is getting divided into IA plus ISH. Very, very important. At this node point, if you apply the KCL, we have applied some voltage. Because of this, the motor draws some current. That current drawn by the motor, some part of it is going to the field winding. RSH is the field winding, shunt field winding. RSC is the series field winding. EB is the back EMF generated by the motor. V is the terminal voltage. Right? Now, here, if it is short shunt, we can observe here at this node point, if we apply the KCL, whatever current that is I flowing here, right? Because of the applied voltage. Now here I equal to some current is flowing to the armature plus ISH. Here also whatever current that is entering at this node point is flowing to the field winding and armature. Separately excited, the field winding is separately excited by some means of DC supply. And if you want to control the flow of current, if you want to control the current flowing to the field winding, we are having a variable rheostat. With the help of this rheostat, what we can do, we can control the current flowing to the field winding. Right? Now here some current I is flowing into the motor. It draws some current. Right? Yeah. So this is with respect to the DC motor. Now, these are the equations with respect to the current. At the starting case, base case, to make you get familiar with the currents, we have discussed only about the currents. But voltages, with respect to the voltages, we can observe that here, with respect to the generator, whatever voltage that is generated from the generator, don't think that it will be entire voltage will be available across the load. How do you understand that? For example, EG, for example, if EG equals to 250 volts, do you think that that entire generated voltage will be available to the load? For example, here if I have connected a load, either a small, any electrical load, do you think that V also will be 250 volts? No, because of the resistance of this winding and also because of the resistance of the armature, out of this generated voltage 250 volts, okay, some voltage will be dropped in the windings of this armature or series field winding, like that. Now remaining part of voltage only will be available across the load in case of generator. That means, how do you understand that? For example, Eg minus in the case of series wound, IA RA is the drop in the armature, IARA out of generated total generated voltage EG. IARA, for example, armature is have field winding is having some resistance RA. The current flowing in the armature is IA, right? Now out of generated EG, IARA is wasted or dropped across the armature. Now the same current is flowing in the series field winding, and the winding is having resistance RSC. Similarly, there also there is some voltage drop IARSC. Then the remaining thing will be available across the load V, terminal voltage V. Therefore, in series generator, EG minus IARA minus IARSC minus V equal to 0. Right? Then if we separate EG equals to V plus, let me take out IA common. IA bracket of RA plus RSC. Clear? But in series generator, armature, series field winding and the load all are in series. Therefore, IA equal to ISC equal to I. IA equal to ISC equal to I. Clear? Right. Now, if you observe shunt generator, out of the total generated voltage EG, there is a drop of IA across the armature. There is a voltage drop of IARA across the armature. In the diagram you can observe there is no any other in series field winding. There is a voltage drop across armature only. Here there is no any series field winding is not there. Only shunt field winding is there. In shunt case, the terminal voltage will be the voltage across the shunt field winding also. Both are in parallel. Whatever voltage is there across the terminal V, that will be available across the shunt field winding. If I want ISH, if I want to calculate what is the amount of current flowing in the shunt field, what is the voltage V? How much is the resistance RSH? V divided by RSH will give us ISH value. ISH value. This I depends upon other factors, right? Now observe. So EG, the generated voltage, if it is shunt generator, EG equal to V plus IA RA. But if you apply KCL in shunt generator, IA equal to how much? Current generated from armature equal to I plus ISH. ISH equal to the voltage across the shunt field winding is V. V divided by RSH. Right? Now, in DC short shunt generator, if you observe DC short shunt, out of generated voltage EG minus drop across armature minus drop across the series field winding is equal to the voltage across the terminal. Therefore, EG equal to V plus IARA plus ISC RSC. But in short shunt, as we have discussed earlier, the armature current IA is equal to ISC plus ISH. Shunt current in all the cases it will be same. ISH equal to V divided by RSH. These are the very important formulas, dear students, with respect to the DC generators and DC motors, right? And these equations are important. These equations are important. While attempting the problems also, we must be in a position to recollect these formulas. Then only we can easily write an essay on this topic. I repeat again, these diagrams are important. Simple. If it is series, draw the field winding in series. If it is shunt, just simply draw the shunt field winding in parallel. Short shunt, RSH in parallel to the armature, and RSC will be in series to the load. Long shunt, armature will be having the series field winding will be in series with the armature, and also you will have the RSH in parallel to the entire combination, long both for entire combination it is having in parallel. Separately excited, easily you can draw this diagram. These diagrams and equations are compulsory for this topic. Then only easily you can attempt the question and you can solve the problems. On seeing itself, you should be in a position to write the KCL. I equal to in series connection currents will be same. Like that we have to understand. On seeing these diagrams, we should write the KCLs, right? Once you know the KCLs, voltages, don't think that entire generated voltage will be available at the load. Some voltage will be wasted. Out of generated voltage EG, you have to subtract the drops. The voltage those are dropped or wasted because of the resistances of the winding. That remaining part only will be available across the load. Like that you remember. Or you can apply the KVL. KVL, or if you write KVL, then also you will get the same equations, right? Once if this base equation is known, remaining things are very easy. Similarly, for long shunt, EG minus IA RA minus ISC RSC equal to V, right? And IA equals to ISC, therefore EG equal to V plus IA bracket of RA plus RSC bracket of RA plus RSC. But armature current is equal to I plus ISH and ISH equal to V divided by RSH. For motor, what happens with respect to the motor? Out of applied voltage, V minus drop across armature, drop in the series field winding, then only that much will be available as a back EMF EB. V minus IA RA minus IA RSC equal to EB. EB equal to V minus bracket of V minus IA into bracket of RA plus RSC. In series, IA equal to ISC equal to I. For shunt motor also, whatever the voltage that is applied, V equals to EB plus IA RA by applying the KVL, and you know the KCL, I equals to IA plus ISH, and the shunt field current is given by V divided by RSH, right? Similarly, for short DC, short shunt motor, V equal to EB plus ISC RSC plus IARA, EB equal to V minus ISC RSC minus IARA, and here the current drawn by the motor I equals to IA plus ISH, and ISH equal to V divided by RSH. For long shunt motor, V equal to EB plus IARA plus ISC RSC, but IA equal to ISC, right? And EB will be how much? V minus IA bracket of RA plus RSC, right? And shunt field current is same. ISH equal to V divided by RSH. So dear students, in this entire discussions, these are all the different variables we have used. V terminal voltage, EG generated voltage, I load current or line current, RSC series field resistance, RSH shunt field resistance, RSH shunt field resistance, IA armature current, ISH shunt field current, ISC series field current. So these are the important variables you have to indicate, right? So uh, next we will discuss about the problems on this topic. Dear students, in this entire discussion, the important things is here you can observe. Generator converts mechanical power into electrical power. The current that is coming out of from the armature IA will be equal to I plus ISH. Whereas in motor, the input current I will be equal to IA plus ISH in shunt case. Like that, you please remember. Okay, thank you. Next, sorry, we will discuss about the problems next. Now, please observe, dear students. Let me do some problems on this topic. A DC shunt generator supplies a load of 5 kilowatt at 220 volt. Calculate induced EMF if armature resistance is 0.6 ohm and field resistance is 80 ohm. Okay. So, dear students, while attempting such kind of problems, right, first write down the data given and also if possible draw the figure. He has specified in the problem DC shunt generator, right? So easily we can draw an armature and have a switch in parallel to that. The current generated by the armature indicating it as IA, current flowing to the field winding as ISH, current flowing to the load IL, like this. This simple diagram will help you a lot, right? A DC shunt generator has specified in the problem. Next, load of 5 kilowatt. So power is given. Terminal voltage. The names of the variables are important because even though we know the formulas, sometimes what happens is this 220 represents which voltage. There the student gets a doubt whether it is EG or V. And also resistance, you know, armature resistance, the variable name armature resistance, it is to be indicated with letter RA. And also specified field resistance. He has not told anything whether it is shunt field or series field, but if you observe shunt generator, so obviously this is shunt field resistance RSH equals to 80 ohms. Like this, from the problem given, once we are comfort to indicate the variable name, then it will be very easy to do the problem. Clear? Now induced EMF EG. If you observe here, with respect to the generator, out of the entire generated voltage EG, IARA is the drop. Remaining thing will be available at the load V. EG minus IARA is the drop equals to V. Right? Now EG equals to how much? V plus IARA. EG equal to V plus IARA. If you observe, if you apply the KCL at this node point, entering current IA equal to IL plus ISH. But what will be the current flowing to this field winding? The voltage across this winding is V. ISH equal to V divided by RSH. V is given 220 divided by 80. Therefore, 2.75 amps flows to the field winding. 2.75 amps is flowing to the field winding. Now, what could be the power drawn by the load? Sorry, current drawn by the load. Load power is given VI. Out of that, the voltage we know already. The voltage across the load is V, terminal voltage. So easily we can calculate the current drawn by the load, IL. Simply power divided by voltage. Now we got IL also. Once we know IL and ISH, it is easy for us to calculate IA. IA equal to IL plus ISH. So total current generated from the armature, IL plus ISH 25.47. Right? So now induced EMF EG V plus IA RA 220 plus 25.47 into 6. So 235.28 volts. 235.28 volts is the voltage generated from the generator. Voltage generated from the or induced EMF EG. So dear students, in this problem, the entire discussion, the key point is the moment you see the problem, please draw a small diagram, indicate the variable names. From the data given, please identify the variables. Power 5 kilowatt, terminal voltage V220, armature resistance RA 0.6 and field resistance RSH 80. Like this, once you indicate with the help of assign to the variables and also known formulas, if you write it aside, then easily you can do this problems. Don't think that only for the final answer you will be awarded the full marks. For procedure itself, we can get some good marks also, right? Similarly, let me observe one more problem. A 4-pole long shunt, he has specified long shunt compound generator supplies 100 amps at a terminal voltage of 220 volt if armature resistance is 0.02 ohms, series field resistance 0.04 ohm and shunt field resistance of 100 ohm. Find generated EMF and the take drop per brush as 1 volt. He is saying that to consider the drop per brush as 1 volt. Now data given 4 poles. Which type of generator? Long shunt. Load current IL 100 amps. Terminal voltage 220 volt. Armature resistance is specified in the problem. RA 0.02. Shunt field resistance RSH 100 ohm. Series field resistance RSC 0.04 ohm. Okay, 0.04 ohm. And from this he told you the long shunt. Based on that we can draw a diagram. RSC in series to the armature, and we are having RSH which is parallel to this entire combination. Terminal voltage specified, load current 100 amps it is drawing, right? Like this, if once we draw the diagram, it will be very easy for us to apply the KCL and to calculate the voltage drops. Now out of this entire generated voltage EG, okay, IA into the resistance of the armature and resistance of the series field winding. And one more thing, he has in the problem he has specified one more extra drop, that is drop per brush. In this motor or generator we are having two brushes, so per brush 1 volt is the drop, right? Now for two brushes there will be 2 volts drop, right? Brush drop per brush 1 volt. Now generated EMF, this is the formula. But what about IA? IL plus ISH. What will be the current of this ISH? The terminal voltage is 220. Here the voltage is 220, right? Now 220 divided by 100. So in the shunt field 2.2 amps is flowing. Now IL already given. IL is already known. This 100 amps is already known. Now what could be this IA? If you apply KCL, entering current is equal to the this leaving current ISH plus IL. That is what we have written here. So the current generated from the armature is 102.2 amps. Now it is easy for you to calculate EG. EG equal to 220 plus IA. Just now we have calculated 102.2 bracket of RA 0.02 plus RSC 0.04 plus 2 into 1. Why 2? Because there are two brushes. Two brushes will be there, right? So for two brushes the voltage drop is 2 into 1 volt. Clear? Therefore, EG equals to 228.132 volt. Like this, we have to do the problem. Clear? Right. Now, let me observe one more example. A short shunt cumulative compound DC generator supplies 5 kilowatt at 220 volt, shunt field resistance RSH 100 ohm, series field resistance 0.3 ohm, armature resistance 0.4 ohm. Calculate induced EMF. Calculate induced EMF. Right? Load already specified, indirectly power V into IL, current drawn by the load. Terminal voltage 220 volt. Shunt field resistance RSH 100 ohm. Series field resistance RSC 0.3. Armature resistance RA 0.4. Induced EMF EG equals to how much? First let me draw the diagram for short shunt. He clearly specified short shunt. So this is the diagram for short shunt generator, right? RSC will be like this present, armature RSH, and this current entering is armature current IA. IA is entering like this. Some part will flow to the shunt field, some part will flow to the load, right? The load is already specified 5 kilowatt, terminal voltage 220 volt. Now EG out of the generated voltage EG minus the drop at armature IARA minus, right, IL, the current flowing in this series winding resistance RSC, IL into RSC will be equal to V. But what about IA? Equal to IL plus ISH. At this node point, if you apply KCL, IA equal to IL plus ISH. IL, power by voltage. Power already specified 5 kilowatt. 5 into 10 power 3 divided by 220, right? 5 into 10 power 3 divided by 220. So 22.72 amps. ISH, the voltage across V divided by RSH. So 220 divided by 100, 2.2 amps. Now what will be the armature current IA? 24.92 amps. Therefore, our generated voltage EG will be equals to V plus IA RA plus IL RSC. If you do the substitutions, you will get around 236.72 236.78 volts. 236.78 volts. That is the generated or induced EMF EG. Induced EMF EG. Clear? Right. Now, let me see one more example, dear students. This is the last example. A series DC generator supplies a load of 5 kilowatt at 220 volt. Calculate induced EMF. Series field resistance is 0.3, armature resistance 0.4. Calculate induced EMF. Calculate induced EMF. From the data given, simply draw a diagram. Armature in series to that series field winding, a load of 5 kilowatt, which is a terminal voltage 220 volts, and the current, some current will be flowing to the load IL. Observe armature, series field winding, and load all are in series. IA equal to ISC equal to IL. IA equal to ISC equal to IL. Right? Now, what happens? Load 5 kilowatt, terminal voltage 220 volt, series field resistance RSC, this one RSC 0.3, armature resistance, right, 0.4. EG equal to be how much for a series generator? Out of the entire generated voltage, there is some drop in the field winding and also in the armature, right? Because of that, EG will be equal to V plus IA bracket of RA plus RSC, because all the currents are same, right? IA bracket of RA plus RSC. Now, in this formula, what will be the current drawn by the load? You know the power divided by voltage, we will get line current, or current drawn by the load. So power divided by 220 will give us IL. Once we know IL, it is same as IA. It is same as IA. Therefore, EG will be equal to how much? 220 plus 22.72 into bracket of RA plus RSC. So 15.904 volts is the drop. That means indirectly how much is generated from the generator? 235.904. 235.904 volts is generated from the generator. Out of that, how much is wasted or dropped? 15 volts is dropped or wasted because of the winding, right? So dear students, like this you have to attempt the questions on this topic. This topic is important. So in this video we have discussed about nearly some four examples on all the different types of DC generators, right? Shunt, series, compound, and here these classifications and the KCL equations, all those things are completed, right? Thank you.